So, we start our third week, and as we proceed you will see the level gets slightly advanced. We have spoken about a gradient vector when we spoke about the derivative of a function in higher dimension f from Rn to R, R2 to R, whatever. We spoke about the gradient. Gradient is nothing but a column vector which consists of all the partial derivatives. So, gradient vector, so if I have a f, say f from R3 to R, so in this case the gradient of f at any point x, y and z is a vector whose entries are the three partial derivatives. So, it is a vector with 3 rows and 1 column, 3 cross 1. So, this is a vector in R3. Of course, these are coordinates, a vector grad f can be f at x, y, z, can be also written in the way which the physicists would like. The physicists would like it to be written as follows, that del f del x I vector plus del f del y j vector plus del f del z k vector. So, physicists would possibly expect a writing like this. So, why are we interested in talking about the gradient vector? The first thing to note about the gradient vector is the following. In fact, it does not matter which space you are in, R3 or R2 or Rn, it does not really matter, but so what does grad f do? So, if I have a function f from R3 to R, grad f picks up an element in R3 and sends them to another element in R3. So, grad f is a mapping. So, grad f is a vector valued mapping. So, in general, if f is from Rn to Rn, sorry, f is from Rn to R, then grad of f, the gradient vector, is also mapping from Rn to Rn. The interesting part is that the domain and the codomain of this mapping are same. Now, let us look at the mapping f from R2 to R. And grad f is a mapping from, so it takes in any element in R2, assuming that the gradient exists. Of course, when I am just writing, you do not take it to be any arbitrary function, you have to take a function for which the partial derivatives exist. So, let us take this kind of function and observe what does it mean. At any point in R2, I get another point in R2. So, if this is my R2, the x axis and the y axis, this is my space R2. Then take any point, at any point in R2, grad f takes this and gives me another vector. So, it gives me some vector in a given direction. So, from here it talks me about a vector in some given direction. Another point, it can show me a different direction, another point can show another direction, right. So, this is full of such, at every point there is a kind of direction. This is an arbitrary drawing taken off from the mind, just to tell you that at every point you can have these arrows. So, basically if you take a large number of points, the field would be like filled with small arrows. So, we say the gradient mapping generates a vector field. The gradient mapping grad f generates a vector field. It is like a kind of you can say why this name field. This field name has stuck on when, from the time when Faraday thought about electric field, that every point in space there is a charge. So, as if the charge seems to flow from one point of the space to other. So, it is like that is what is called the velocity field in mechanics, that if a particle is moving in space, then at every point there is a vector which is tangent to the path of the velocity vector is tangent to the path of the motion of the curve and motion of the particle along that curve. At every point when you take the tangent, you generate the field of velocity. So, the velocity field is a vector field. So, that is again generated through a gradient mapping, right, or the derivative mapping. It is a very simple. For example, let us take an example right out of this book which we are referring continuously, the book again by Marsden, Tromba and Weinstein, that is the standard book which we have been using from the very first day. So, if we want to take a function f x y, so from R2 to R2, and let this function be the most simplest one, simplest looking quadratic one, x square plus y square. So, grad of f at x y, I can write it in the physicist style as 2x I vector plus 2y j vector. Now, let me try to draw the field. Okay, this is x y. Now, let me look at the point 1 1. At the point 1 1, the gradient vector is 2 2. So, gradient vector is 2 2. So, the gradient vector points in this direction because 2 2 he is here. So, gradient vector is 2 2. So, this is your field at 1 1. So, for example, here grad f 1 1 is 2 2. 0 0 it remains at 0 0. Suppose you have half half, it is 1 1. So, if it is half half, if it is half and half, then the field is here. So, at any point you have a field. So, suppose it is suppose I take it as 3 2, right. So, this is 3 and 2. So, suppose this is the point 3 2. At this point, where is the vector field pointing? Put x is 3, it will be 6 and then y would be 4, 6 4. So, you go 6 and some direction this. So, it will be pointing somewhere like this. So, at every point, you know, you take a point like this, it will point in this direction. So, you can take a little bit of time and have some fun sketching the vector field of this particular function. So, what we did was we just tried to draw the vector field. Of course, there is infinite points, you do not try it at every point, you can't spend lives and lives and lives, many lives are insufficient to do it. That is the whole notion of infinity, that it is so incomprehensible, but so useful. We just try to draw the vector field of grad f, draw the vector field of grad f. That is it. This is what we try to do. Now, I give you homework of a very useful computation of gradient. Sometimes computing gradient is very, and this computation is important for physics. Consider the radius vector of a particle moving in 3 dimensions. We have already studied how particles move in the very beginning and made vector representation. So, if you have forgotten, for you to just remind that okay, here is a kind of particle moving through space and here is the radius vector, and this point has coordinates x, y and z. This is the origin, the x axis, y axis and the z axis. Some people also call z as z, it is up to you, but I will always call it z. Corresponding to there, I construct a small function r, which I call as mod r, the length of the vector r, and that is root over x square plus y square plus z square. This is my f of x, y, z. You can also call it r of x, y, z. So, if you want to be more, you do not want to get this f business in, you just call it r of x, y, z is root over x square plus y square plus z square, and you know this is simple. Now, I am giving you the homework. Homework is important. I simply hope that you really do it. If you are sincere about the course, you will try to do it. So, gradient of the mapping r x y z, it is 1 by r x y z into the vector r, that is 1 by r x y z scalar multiplying the vector, which is x of I vector, y of j vector, z of k vector. You can compute this, you can try it out computing the partial derivatives. Also an important one is and in this case the answer should be minus 1 by r x y z whole cube into the vector r. I am not writing the remaining part, you can easily figure out what we have to do. Now, let us focus ourselves on something called a chain rule, and we will see how the chain rule brings into fore the idea of a directional derivative. So, chain rule associated with gradients, chain rule. So, you might say, oh come on, another chain rule. Yes, another chain rule. My God, you must be worried what's happening. Another chain rule is this. So, we will take f to be a function of 2 or 3 variables. This is just for your visualization. It does not matter what the number of variables. Let me tell you. To have chain rules, you do not need really the number of variables can be very different. But let me just for simplicity, for visualization, just let us be restricted to this. Now, CT let CT, maybe I should write tuk another chain rule, okay. So, let CT be a curve on the plane or a curve in 3-dimensional space. Let h of t be f of CT. CT has x t, y t and z t, the curve is defined by that, right, and CT has 3 coordinates. So, x t, y t and z t. I will tell you in details. Let this then, assuming differentiability of everything f, c, everything, dh dt, ddt of h is equal to the gradient of f evaluated CT dot product with the derivative of this curve CT. So, let us see what does this mean. So, you are telling that there is a curve CT along which say a particle is moving. So, this curve is given. So, at any point here is defined by x t, y t is defined by a parameter t, z t, and this any point is a CT. CT is actually the radius, nothing else, the CT, the position. So, that is how what defines the curve. Now, you know that C dash t is nothing but the derivative of C basic is dx dt, dy dt and dz dt, that is it. See, if you look into this whole thing, this is basically a dot product you have to do with the gradient of this. But okay, what is the gradient of this? So, gradient of f at CT means gradient of f at xt, yt, zt. Basically, this is nothing but I am just writing it as a row vector, we can write it as a column vector also. Sometimes I write it as just for the space, maybe I should write this also as a row vector, because you might not be able to see because the table seems to block. So, let me just write it as this del f del x del f del y del f del z. Obviously, each of them can be that is how you basically take the gradient and evaluate the gradient at the point x t, y t, z t. Take it with respect to x, y and t and evaluate, or now you take the dot product of these two, and that basically dot product is a kind of del f del x here evaluated at x t, del f del y evaluated at y t, del f del z evaluated at z t, and then take the dot product evaluated at t. So, this if you write it down in more details is del f del x evaluated at c t into dx dt plus del f del y evaluated at c t dy dt plus del f del z evaluated at c t into dz dt. That is it. That is just what dot product means, and that is exactly what you will do. So, let us take a small example exactly from the book. So, even somebody who has a book can actually check it up. Let us just do it as if we are in a class. So, let us see. So, we will consider the function f x y z example of using the chain rule. So, let us say f of x, y and z, which is evaluated, it is written as x y minus z square, where c t is given as, so x, so sin t, x is sin t, x t is sin t, y t is cos t. These are all t, there is a t which we have not written explicitly, this is E t. Now, what I do? I evaluate, now I call this, so u is f of c t. I want to compute du dt. So, I will just do whatever I did on the board, you see, I will just have a look at the board and I will just first compute them individually, del f del x, del f del y, del f del z, and evaluate them at the point sin t, cos t and E t. So, what is my del f del x? My del f del x is y. So, y would be now evaluated at that point. So, basically which means del f del y is x and del f del z is minus 2z. Now, c dash t, which you know very well, is cos t minus sin t and E t, just taking the derivatives. Now, I am taking the inner product. So, du dt, now when I take the inner product, what I get? When I am taking the inner product, I will put in place of y, I will put cos t. So, it will become cos t into cos t. Then I will put x, I will sin t into minus sin t, because they are evaluated at the point c t, and then I will put E t, that will become minus 2 E t into E t. So, it will become cos square t minus sin square t minus 2 e to the power 2 t. So, this is how very simply using the chain rule we have been able to compute the derivative of this function when given that the x y z has this following pattern. In fact, u can actually be viewed as a function of t itself. If I put here this can be written as sin t cos t minus E t square, and then if you take the derivative du dt, this is exactly what you would get as the derivative. Okay. Now, we shall come to a very interesting idea of directional derivative. This idea of directional derivative works even when you are in higher dimension, but we are not going to talk about the higher dimensional issue now, but we are going to talk about the higher dimensional issue when we are talking about maxima and minima, which will come very soon. But let me just remain in the space R2, R3 is fine, but let us just be in R2, function of two variables, and let us try to look at things. So, consider a function f from R2 to R. Take an x, take x element of R2 means you are in the plane, and any v element of R2. Take these two things. Define the function you could choose v to be a unit vector, that is one which has norm of v or length 1, norm v is 1. Define the function h t as, so you have a t which is in R, f of x, so x is fixed plus t v. So, define a function like this. Define a function like this. So, what is f of x plus t v? Let us understand this whole terminology. I always put things on a positive interval this side R2 plus, it's just because just as a matter of habit, you can put it anywhere. Please understand, it is just a matter of habit. So, take a point x. So, here is the x vector, and take another vector v, so like this. V is a vector, x is a vector. I am not putting the arrow on the top where I should, but I am assuming that when I say v element of R2, I am basically talking about a coordinate, and that coordinate represents the vector. What do you mean T v? T v means, suppose t I take is greater than 1 for the moment, means I have pulled this vector v to some point T v t. So, now this new vector has become T v whose length is t times v. Now, x plus T v by the parallelogram law. So, I will have to draw a vector from x, starting from x, but parallel to the direction of v, and then from the point of T v you know how to draw a vector exactly parallel to x. This new vector is x plus T v. So, what I did, I am moving from x along the vector in the direction of vector v and have moved the distance T v away from x, that is the meaning. So, essentially if I take T to be negative, I can come in this direction. So, basically when I am talking about this point x plus T v, what I am doing is I am moving along a line passing through x, along a line in R2 of course, passing through x and parallel to v. to the vector v. When t is equal to 0 means h0 I have fx. I have fx when t is equal to 0. So, what is my Ct here? So, we are again using the chain rule. So, what is my Ct? Think of it, your Ct in this case is x plus Tv, and this implies that my C dash t is V. So, my rate of change of the function along the direction x, see when I am talking of the function ht is a restriction of the function f along this line which is passing through x and is parallel to the vector v. So, is in the direction of the vector v. So, what I am trying to say is that C dash t tells you at what rate you can move along this line. So, it is as if the velocity along this line would remain a constant, this velocity vector would remain constant. So, you are basically kind of moving along the line with constant velocity, you can think in that terms. So, what you are doing here, you are now going to ask how is the function changing at x, what is the instantaneous change of f at x. Just we talk about instantaneous velocity of a particle at time t, we are talking about an instantaneous change of the function f at x, because as I move from x to x plus something x plus tv x plus, as we move, when as we move between x and x plus tv, the function value keeps on changing. So, what is the change at x? So, my question now is, find the instantaneous change of f at x. So, what I do? So, I take the derivative of h, and if I put t equal to 0, I will get back I am at the point x. So, basically I want to now know what is the dh of dt at t equal to 0. To my joy I will just do the chain rule, grad f of Ct dot C dash t, but I want it at t equal to 0. So, my instantaneous rate of change of the function f at the point x, because when I put t equal to 0, x plus tv becomes x, is nothing but grad f of C0 dot v, which is nothing but grad f of C0 is nothing but x, grad f of x dot v. This rate of change is often called the directional derivative of f in the direction v. So, it is the rate of change of f at the point x in the direction v. So, what is this? So, it is let us rate of change of x, rate of change of f, the function value, rate of change of f in the direction v at the point x. And voila, this is what is called the directional derivative. So, this thing grad f x v, grad f of x dot v is called directional derivative of f in the direction v, directional derivative of f at x in the direction v or along v, direction v. So, here we reach our definition of directional derivative. I ask you a simple question and you really need to answer me this. Before I tell you something, I will tell you a little bit about how gradients behave in respect to level surfaces. I will just ask you a very simple question. Please take it as a homework. I will ask my TAs to look into the lectures and I will ask them to put the solution, or if you think that solutions are not required, fine. If you ask, the solutions, we will give the solutions. The homework is simple: in which direction f is increasing the fastest and in which direction Vf is decreasing the fastest. In which direction, this very question has a deep link to the subject of optimization, the part of mathematics which deals with the maximization and minimization of functions, in which, so this is very important, in which direction f is increasing the fastest the most and in which direction it is decreasing the most. Today we will not go to talk about anything more on this electronic board, but we will go to the blackboard and try to explain a very important thing about the structure of the relation, how a gradient of a function behaves with the surface associated with the function. Take any surface and take any point x0. How would you define a tangent plane to the surface S at x0? So, defining tangent plane, how will you do it? It is not a very difficult job if you just extend your imagination a bit. So, at through x0, think of smooth curves. I am just drawing them like dots, but they are essentially smooth curves passing. So, to every smooth curve, take another smooth curve which is passing through x0. So, to this smooth curve, the first one, I can draw a tangent line. To the other smooth curve, I can draw another tangent line. Similarly, I can draw uncountably infinite such tangent lines, and that tangent lines form what is called the tangent plane. So, it is not a very difficult thing to define a tangent plane. So, basically consider a function, consider the set of all x, y, z, that is the level, consider a function in 3 dimension f from R3 to R. Consider a function f from R3 to R and consider the level surface alpha of f. The level surface. So, what is the meaning of the level surface? Level surface means the set of all x, y, z, z which is in R3 such that alpha is my required parameter here, that is the level at which I am setting it, f y z x z is alpha. So, I show suppose that that is represented by this surface, this is the level surface. So, basically what is happening through each through x naught there are curves we parameterized by t, Ct is passing. Now, what direction or what relation does the gradient vector at x naught. So, this is x naught, maybe I should make it right at this point x naught means it is in 3 dimension, maybe I should write this as some point x naught, which, or maybe x naught is actually a point in 3 dimension representing the vectors x bar, y bar and z bar. Okay. Now, what is, if I want to compute the gradient of f at x bar, y bar, z bar, in which direction it is pointing, is there any relationship of the direction with the surface? Is there any particular relationship? This is the question that we are going to ask ourselves now. Let us see what we get out of it. So, take this curve as CT, consider this curve, this curve whose tangent line I have drawn. This curve, let this be given by CT. Then, because this curve lies completely on the surface, and for that surface any point on that surface has to satisfy this, I have f of CT is equal to alpha. So, if I take the derivative with respect to t, I will have 0 because this said. So, basically, so if I call this as ht, I know that dh dt is equal to 0, and again I know by the chain rule dh dt is grad f of CT, right, dot c dash t, and that is equal to 0. And at what point I am computing it? I am computing it at the point x naught or x bar, y bar, z bar, which is the t bar. So, x bar t, right, I am computing it, x naught means where x, basically I am computing x naught actually means the point, suppose on the curve CT x naught, x bar actually means the point x t naught, y t naught and z t naught. So, this is actually your x bar, this is your y bar, this is your z bar. So, there is a t naught with respect to what it, which corresponds to these values x bar, y bar and z bar. But if there is another curve C1t, there may be some other point t0 dash where x, you have this kind of correspondences, but the x bar, y bar, z bar is the same point because it represents the same point x naught vector in R3. So, now what happens, what did you get? So, here, so this is dh dt is equal to 0. So, at this particular point if you want to evaluate, so at t naught, so t naught you will get 0. So, if you evaluate it at t equal to t naught, you will get 0, means at this point c dash t naught is tangential. C, if Ct is the curve along which the particle is moving, for example, on the surface, then c dash t naught is its velocity, and this is 0, the dot product is 0, which means we have already shown earlier that the direction of the gradient vector, your c t naught is nothing but x naught, your c t naught is nothing but your x naught. So, your grad f of x naught is just perpendicular to the c dash t naught, but c dash t naught is lying on the tangent plane because it is tangent to the curve CT, it is lying on the tangent plane. So, if at a point where the tangent plane touches x naught, since it is perpendicular to one vector of c dash t naught, the grad f x c t naught or grad f x naught is perpendicular to the tangent plane at x naught, which we have taken the convention that if a vector is perpendicular to tangent plane at a surface at x naught, then we said that the vector is perpendicular to the surface at x naught. Hence, the relation between the gradient of f at x naught and the surface is that the gradient is always pointing perpendicular to the surface. This is possible because of this simple chain rule that we had done, and this is so simple that the chain rule is actually elucidating the geometry, and this is something which you really have to keep in mind. Thank you very much. I hope you had a good time, as I had a good time discussing this with you, and in the next class we are going to talk about a very important thing, implicit function theorem. Thank you.